All right. Cool.
Hey.
I guess I just had to make it live. All right. So, right now, damn, I sent out invitations and now nobody's getting them. Yay. Okay.
Hey. Okay.
What's up?
I can hear you. Were you hearing me?
Yeah, I can hear you fine.
All right, cool. Real discrete arrows go up, click like.
Yeah, I was discreetly trying to get from.
They say the big three questions would be probability, induction. I don't remember. Probably dividing.
Okay.
What did we learn in assignment 5 again?
Oh, pigeonhole principle.
Pigeonhole, yeah.
Hold on 1 second. You're gonna be alone for a little bit.
Man, I can't believe AKA Cartoon. Did you watch Ed and Eddie back in the day?
Hello.
Hello.
Hi.
All right, looks like we got a bunch of people. Ugh. All right, who can hear me and who cannot hear me?
I can hear you.
I can hear you.
I can hear you too.
Yay, everybody! This is so fantastic. All right. Okay, and so for people who are not on the stream and just watching, you can answer questions. There's a Q&A section that you can jump on, and hopefully I will try to answer it as thoroughly as possible. Where am I? Big book of stuff. And I just got back from work, so I'm like rushing for everything. I'm like, ah.
That's okay. No worries.
There we go. And there's that. Okay, so I remember from the last study group that there were the 3 big questions.
Yeah, there's 3 big questions and then 15 like short answer ones.
Yeah.
Yeah. I remember this time he said like for the 3 of them he said one of them would be probability, one of them would be induction, and I can't remember what he said the other one would be, most likely.
Probably number theory.
Oh yeah, true. Yeah, that's what it was.
I'm relatively certain it's going to be number theory.
Maybe like a multiple part number theory, because the number theory part didn't really seem to be that hard this go around.
We got Harold saying it's number theory divided halfway. What does he mean by that?
Euclidean and divisibility.
Plus divisibility. Okay. That makes sense. Okay. So, I guess, like, the easiest one for me, that's what I recall as well, the easiest one for me would probably be induction, because it's kind of straightforward.
Yeah.
I mean, it's just step by step, it's easier.
Yeah. And then probability, I think I have the biggest problem with, because it's kind of like it's just like, what was it? It was just like counting, where there was multiple ways to get to the same solution, and you're not entirely too sure if you're right or not, which is like my big problem, because I would like math to have only one solution and one way to do things, and then that's it. You know.
You like physics?
I do like physics. Physics is nice. It's great.
That's math with exceptions, though. You've just broken. That's math with exceptions, like probability.
Okay.
Totally.
Disagree.
Oh, all
I
right.
see how it is.
Fine. I see how it is. All right. I guess I don't like probability because it's just it's not intuitive to me in a sense.
I've done a lot of, I mean, when you do game dev, you do a lot of probability-related stuff. I mean, I just found it like pretty easy. You just take the probability, you just look at all the possibilities. The possibility that, like, you know, what's the possibility that a queen is in a chess piece set, and that 6-piece set? You do 1, then you say, like, if there's like 4 pieces, you do 5 choose 3. You choose 3 from 5, and then that's your answer. And then you divide it by the amount of pieces you have. That's 15.
Yeah.
So let's do this. Where am I? Where's the homework?
Does my webcam look like a rectangle while all you guys are squares?
No.
That's
Mine-
just how it is for your screen. Like,
Okay.
Your bottom screen is a rectangle, while when you're talking it becomes a square.
Yeah.
Because
Yeah.
I think I haven't locked you yet. Depending on if I decide to lock just you. You know.
That's fine.
I think I have the ability to do that. I don't even know.
does anyone have any examples of like example problems for discrete random variables? Because
Discrete random variables?
yeah,
Let me check web courses. Maybe
Oh,
it's
so
in
you're
there.
talking about like when you flip like a coin 3 times, right?
yeah,
Like your discrete random variable is the event that the coin flip happens 3 times. So if you get heads all 3 times, it happens to be 3. If you get heads, tails, heads.
yeah.
Yeah.
Like I don't know like what kind of I don't know what kind of problem he would give for us, but I don't know. I'm kind of iffy on that.
It'd probably be like that. It'd probably be like that coin flipping one, if anything.
Yeah.
See now, assignment 6. No, that's not what I want to see. Go to pages.
Let's see if my tablet's working today.
That's what I'm trying to set up right now.
You guys want any trail mix?
Oh yeah.
Comics.
I'll take
All
some.
right. I'll send it through the computer.
Thank you.
That's not trail mix. That's fruit and nuts. You lied to us.
Oh yeah, lies.
I thought they were the same thing.
So not.
It says trail mix on the. It says trail mix on the thing. Whatever.
The bag full of lies.
The bag full of lies. Okay, let's do. Let's
If you have a bag full of truths and if you have a bag full of tautologies and contradictions, what's the probability that you'll pull out a tautology?
Are they evenly weighted?
It's kind of like it's 70-30.
It depends on if you're an optimist or a pessimist.
Yeah.
You know, we just went existential on that one.
We did philosophy and math. It was a fun kid.
Ooh. Okay, let's see probability. Because that's when we saw the discrete random variable, right?
Oh yeah, discrete random variables. Let me check the
I know I'm being sarcastic.
This.
But yeah, I thought. I'm sorry. I'm being silly. I'm
It would
sorry.
be in probability part 2 of 3.
I'd like to amend my previous statement. Philosophy and math, who would have thought it?
The Greek philosophers who created a lot of the math.
I said thunk the first time, and I got reprimanded for it, so I'm amending that.
So for Okay, where am I? Assignment number 7, the very last one is problem 7. That's one dealing with discrete random variable.
Yeah.
With,
Yeah, I guess that. I mean, the expected value is pretty easy because you just like multiply, the probability by the number. So I mean, that's not too.
yeah.
I mean, I don't know. Would he? I was just like thinking. Like, I don't know. I just feel like he would give us a harder problem, which is what I'm scared of.
Hmm.
'Cause that one's not bad at all. That's
Okay.
forward.
Yeah, that makes sense. I mean, like, I'm trying to think of like what would be a good problem that you would.
I mean, like, I don't think there's going to be that many problems with the state and the test to begin with, but I just want to be prepared.
True.
Yeah.
Let's see. Probability. If I'm a
I honestly prefer doing generalized Bayes theorem to regular Bayes theorem.
Hmm.
I just think it's easier, especially for problem number 2 on assignment 6.
What's the difference between those two again?
The main difference is that it's instead of in the denominator where you do probability E given F complement of F times the complement of F, you instead do the probability of all the other events happening, and then you just add them all up.
Okay.
For number 11 on his study guide, he said, or not number 10, he said, like, could you model a problem using a discrete random variable if asked to, such as the example seen in class, with the expected number of heads when tossing a coin multiple times? And then he said, solve for the probability if it's not given explicitly as the problem 7 on assignment 7.
Yeah, so what he would probably do is say, like, assign the number to the amount of, like, the amount of x you will get of y. What's the probability?
Like, what do you do to find the number and stuff?
He'll usually explain, like, it depends on what the problem is. Like, he'll say, like, find the amount
Find
the amount of heads flipped in 3 coin tosses, or find the amount of pieces that move diagonal in, like, the 6 chess pieces. So, in, like, a set of 4. So, if you have all the pieces that move diagonal, which would be, king, queen, pawn, and bishop, that would be 4. If it's just 3 of those given, that would be 3. If it were just 2 of those, it'd be 2, and if it were just, well, it can't be just 1 because there's 6 pieces, but if it were just 1 of those, it'd be 1.
So
and
the
then you say,
is just like the number of pieces that would move diagonally or whatever in that case?
Yeah, and it's like, if you have, what's the probability that this will be 4? It's 1 out of 15. What's the probability that it'll be 3? You have a lot of different sets, actually. It'd be something divided by 15, and then, let's just say 7 divided by 15. And then, what's the probability that it'll be 2? That's another 7 divided by 15.
Okay.
Actually, there's only 2 pieces that don't move diagonal. You do 4 choose 2. That is 6. So the probability that it'll be 2 of them is 6 out of 15. And then you use that for the rest of them. That would mean it'd be 8 out of 15. I studied for this over the entire weekend, and also Wednesday, Thursday, and Friday. So I feel like super chill about this.
Well, that makes one of us.
Yeah, I feel like I don't know, I feel like for this class it's kind of hard to study because I go over the homework assignments and notes, and then it's like, I don't know what else to go through.
I just review it with myself. I try to remember the homework assignments from memory and try to, like, calculate in my head, like the probability of A intersection B. I think, okay, it's a probability that A and B will be in, will happen. So what you gotta do is make sure that, so you gotta do is, just see, like, okay, the sets where A is. And then you see the sets of A that also have B in them. And that's basically what you do. And then like A union B, you look for the sets that have either A or B in them. Like in the chess pieces one.
Yeah.
If you have king and queen, you look for the sets that have king and queen, and then you have 4 choose 2 for the rest of the pieces. That makes 6 out of 15 or 2/5. If it's king union queen, am I talking too loud?
No.
No.
Okay.
You're fine.
If it's king union queen, you look for the things that don't have, because there's a lot of sets that do have it. You look for the sets that don't have king or queen, and there's only one. So you take the composite of that, which would be, the original is 1 out of 15. You take the composite of that, that's 14 out of out of 15.
Yeah.
And then yeah. What I feel like I'm a bit rusty on is the probability of E given F.
Mhm.
Like I get that it's the probability of E intersection F divided by F, but is it always that though?
Hold on.
Or is that one of those? It depends if they're dependent or not.
You have a point. No.
The best part though about this class, as I said before, is being able to do cool emoticons.
Always good idea to have cool emoticons.
Yeah. I'm
That
gonna
was
make
a
some.
really good one. I was wondering if the intersect of the empty set intersects empty set, is that still the empty set? And then some guy was like, oh, that makes a really good emoticon. And I'm like, that's right, that is a good emoticon. And then you mentioned that later, and I'm like, that is still fantastic. Why isn't this working? But
Alien smiley face.
Okay, Bayes theorem. Okay.
It's not Bayes theorem though. It's E given F.
Oh no, sorry, I was looking at the notes. I was kind of being all weird. Let me think. Okay, so we have probability, number theory, ability, number theory. There's going to be one that I'm pretty sure there's going to be some chess pieces on there.
Yeah.
So I
Like
think,
what I did for oh, sorry, did I interrupt you?
no, go ahead.
Okay, no, because I want to explain my process for number 2 on the assignment 6 that I did with generalized Bayes theorem, because I didn't even think I used Bayes theorem, but here's basically how I did it. So John Aaron is poisoned by the dart given. Now let's say the device is at Renly's seat. There's a 44% chance of that. So we say there's a 44% chance of him noticing it. But no, it's like Renly has to notice the device. That's a 34%, and Renly uses the device on John Aaron. That's 16%. You multiply those together, you get 2.39%. And that's basically how E given F works. You multiply the probabilities together. I think that's how it works. Yeah.
if it's independent. If it's not independent, then it's
Yeah, if it's dependent, you multiply them together. Right?
if it's independent, you multiply them together.
Oh. I still got the right answer. Cause like the
Is it
device,
graded yet? Did the TAs catch that?
no, cause it's like the device is at Renly's seat 44%. Renly notices the device 34%. Like that 34% is within is 34% of 44%. So you do multiply it. Because it's within that. Like once he notices the device, there's a 34%. Like once the device is at his seat, there's a 34% chance he'll notice it. it's 34% given that he notices the device, which there's a 44% chance of. So you do multiply it, and then you multiply it by 16, and then you get 2.39%.
It technically makes sense, but I think he was looking for us to do it with his theorem.
Like, there's a way to logic it out, I'm sure, but I know that if it's
This is a
independent,
logic class.
yeah. Yeah, you're right. But I mean, like, I'm sure that you could like pictograph your way through the thing. But
I mean, as long as you get to the right answer in the right way, like, you know.
the right way, yeah. Because, yeah.
Is there any way we could go over those logic trees? Like, I don't know, does anybody else have, like, logic tree examples? Because I kind of, like, suck at throwing those.
Yeah,
the
me too.
trees.
Yeah, the trees. I hate those trees.
Do you have a specific example that you want to go over?
Oh, gosh. Well, I don't have, like, a specific one, but, like, I mean, he said we have to be able to, like, draw them and take information from them, so I don't, like, I'm sure, let me try to find one from his notes.
Okay.
I'm assuming they'd probably be with the probability notes.
Yeah.
Yeah, I'm pretty sure it will be. Ooh, Fazl's here. I don't know which one Fazl is. There he is.
I was already here, but like I don't know. I just kicked me for a second.
Yeah, Google Hangouts likes to do that. All right, real quick. Let me just answer some questions.
Wait, how do I unmute people? Some people are muted for some reason.
I think you.
I think they have to unmute themselves.
No. Fazl muted Vark by accident, I think.
Oh, okay.
Yeah.
So there's going to be like, in their box, there's going to be like a little thing where you can like mute or unmute. Right now, if they're muting themselves, they can only unmute themselves. But if you mute the person, like for instance, I can mute Swathi real quick, and then I won't be able to hear her. Or I can eject. Oh wait, I think that's just me, actually.
Okay, for the probability part 1 notes,
How do I unmute?
yeah, there's a tree.
Probability part 1.
Yeah. If you go to like his written notes,
All right.
the page 7 of the PDF.
And
Let's explore the idea of independent events through probability trees.
oh, okay.
Yeah.
So for instance, Vark, do you have like that tablet up? Because I couldn't figure out how to work my tablet on my computer, so I'm kind of like.
I have no idea how to do that.
Let's do this.
That works.
But essentially, what you're doing is, let's say, for instance, you have a specific event, right? In this case, it's 10 motors. 3 of
Oh
them.
shit, my thing was muted. I didn't even realize. Do you mean this? You mean this tablet?
Yeah, your Wacom tablet, so you can write on stuff.
Oh, you want me to open up Sci?
Yeah, could you be our whiteboard?
All right, sure.
Be the scribe.
I'm surprised they don't actually. Oh wait, let's see if they have a whiteboard app.
Ooh.
They do.
Oh snap.
Oh wait, this one says draw, but it just says like draw on each other inside a Hangout.
Yeah, that's interesting.
Let me see. Let me just search. No, they don't have a search function.
Okay.
Let me see if what's this Google Art project? Join Google Aspiring Artworks. No. Let's see this. Install Hangout expansion. All right. Well, I'm gonna try something super quick. Oh shit, my tablet isn't plugged in. Let me plug it in. All right. If your tablet isn't working, it's probably an issue with the drivers.
Yeah.
This user was not running draw. You have to, Swathi, could you run draw also? Okay, you go to you see on like the sidebar, you go, there's like 3 dots.
Gosh, if her webcam's not on. It's dependent on the webcam.
Oh, okay, hold on. Let me try you then. It says you're not running draw also, hold on, let me do something. This user...
Run draw. There, I've run draw.
I mean, do I need to draw? I can just watch other people draw.
I need another person to use it so I can draw on them and then use them as the
Wait, what were
whiteboard.
you doing last time? You were like, what were you using to draw?
Alright, I'll open Sci. I was using a word
this might be
program.
easier.
Let me open up Sci right now and then make a big canvas. I just remember last time I did that I got super distracted and I ended up getting a C on the exam, so...
Oh, snap. Well, don't draw the things that you were normally drawing.
Yeah. Let me
You got
just...
distracted for what?
Shit. Oh, here it is.
You ended up drawing like some anime.
Alright, do you guys see?
For an hour.
Do you guys see?
Hold on 1 second. Yes, I see you.
Okay.
Okay, so it's the probability notes, the part 1, page 7.
Okay, probability part 1, page 7. Let me open that right now.
It's the tree, the probability trees. R, the event where I go for a run today. S, the event where it snows today.
Okay, let me open that right now. No, don't do this to me.
Wait, I thought you were talking about the
Don't be
boulders.
Which one? Wait, which one were you looking at?
Okay,
I was looking at the boulders.
so what happens is like I say, the probability, like, it's very easy to do. Like, you say, like, okay, we could say that, like, we have a 6, let's say, we have a die. Let me just draw a die right here. Okay, let's say we have a die, and, we don't know what it's gonna land on. We know that we have a 6. Shit, I could do that better.
The drawing doesn't really matter that much.
Yeah, but I like. Okay, so we have 1 6 1 6 1 1 2 1.
1 6 all around, yeah.
Yeah. So now let's say let's just say we're looking for if it's odd or even.
Okay.
So then
Probability that it's odd.
break it into 2, O, E, and we say that there's a half chance of it being odd and there's a half chance of it being even.
Yep.
Now, let's say the next roll has another half chance of being odd or even, and it just keeps going and going and going. Now, let's say you can't roll. Now that's
Wait, but if it has a half chance of being odd. Oh wait, never mind. Okay.
Yeah. Sometimes I don't know if you ever heard of the talking to a rubber duck, but sometimes you have to just say stuff and like talking to people to realize where you
For some
made a
reason, I was
mistake.
thinking of his orbs like thing that he did in class, and I was like, wait, if there's like 3 blues and 3 reds, I mean, if you take 1 like red out, then there's gonna be. Yeah, I was just.
So that's with replacement. But let's say we can't roll the same number twice.
Yeah. Okay. So that's.
We already rolled 1 odd, so we roll another odd. That is
It's like 2 out of 6.
Yeah.
That's like wait, no, because there's 3 odds. That's 1/2. It would be 1/3 actually. You're right, 1/3.
Yeah.
And then another even would be 1/2. And then same thing here, but with them reversed. Then we do another odd. It's like O, 1 6 E 1/2. And then we have O 1/3 E 1/3. And notice how these technically add up to this is 3 6. Then we have either a 2 6 chance or a 3 6 chance.
Yeah.
These add up to no, these 2 branches add up to a whole. And these 2 branches add up to 5 6. And
Yeah,
both of
5,
these
6,
2
5,
add up to 4 6 each. That has nothing to do with anything. I just found it interesting. I like little logic stuff like that.
So like when he gives us a tree, like what questions could he ask that we would have to like figure out? Like, does that make
You
sense?
have to probably plot it out.
Well, yeah. So like one of the things that he could ask us to do is given like a situation, we would have to draw the probability tree. But he could also give us like a probability tree and ask questions. So like, what kind of questions do you think he would ask, like for us to calculate from the probability tree?
So let's say for instance he had like a question like there's three red motors.
Yeah.
And there's 4 blue motors.
Yeah.
Right. Draw a probability that on the first 3 times that you pick without replacement,
Okay.
that you'll get red motors each time.
Okay.
Or maybe he'll show a tree with replacement and ask you to do it without, or vice versa.
Yeah, he could do that as well, but you have to remember.
If he gave you a tree like showing with replacement, like how would you like? I don't know how would you like to change that without? Would you basically just have to like redraw the whole thing starting from the first numbers?
Yeah.
Yeah, the first starting branch of the tree would be the same, but the branches after that would all be different.
Yeah. And real quick, James Anderson is asking, aren't all the branches supposed to add up to 1? And yes, they do.
Well, that's with replacement, but without replacement, they add up to however many choices are left.
Exactly. So like when you're doing the second iteration of this tree, right? You're doing it out of fifths instead of out of sixths. So I think that's where he's kind of like getting confused. So I just wanted to answer that real quick because I think that would be like a very common question.
Stupid question. Which is it with replacement or without replacement that order matters?
I think it's without replacement that order matters.
Okay. Oh yeah. Okay, that makes sense.
Mm-hmm.
Yeah. Actually, no. With replacement, order matters because without replacement, you're only going to have 1 of each. In like a set of the chess pieces, you're only going to have 1 of each without replacement.
Oh.
And then with replacement.
So without replacement means that order matters.
No.
With.
No. Think of it like okay, so there's a branch. Let me can I draw on the screen?
Do you have your draw?
Wonderful. There's like a branch. Okay, so think of it like you have the first level, right?
Yeah.
Do you have with replacement or without replacement? If it's without replacement, then you go do other things. If it's with replacement, then you do the multiplicative rule. How many ways can we do the thing? You know. So in the problem, we had sets. We had a cardinality of 6, right?
Yeah.
Or a cardinality of 4. So there's 6 ways you could pick the first spot, 6 ways you could pick the second spot because we're doing multiplicative rule. We're doing with replacement. If it's without replacement, then you go to the next subset. Does order matter? Does order not matter? Right? Without replacement is in both subsets, but they're different. If order does not matter and it's without replacement, then it's combinations.
And if order does matter and it's with replacement, it's a permutation.
No. If it's without replacement, and so if it's without replacement and order matters, then it's permutations, right?
Wait,
so order matters permutations.
Say that again. Sorry.
Order matter permutations. Order does not matter combinations, and that both of those are without replacement. With replacement, totally different subset. You're doing the multiplicative rule. How many ways can you do stuff?
Okay.
So, statistics.
This link I'm about to post in the chat actually explains it pretty well.
Yeah, it's like better with the branches. I'm trying to get my tablet to work, and it's not.
With replacement means the same item can be chosen more than once, and without means that it cannot be selected more than once. So with replacement, order does matter.
Yeah, that makes sense.
With replacement, order does matter. Yeah. Okay. Cool. Did I answer your question?
Does
I
anything
think this
matter?
test is gonna hopefully go better than the last one.
Yeah, same.
I feel like there are less like things to memorize, and it's more just like figuring things out. I guess.
Yeah.
Yeah.
But I guess I don't know. That could mean there's more ways to go wrong. I never know with these tests because like I feel like the test questions are like similar to the homework problems yet completely different for some reason. Like maybe that's just me.
No, you're. Well, it depends. Like they're not totally different. They're somewhat related, but I mean there's a stark contrast.
There's like I feel like because the homework problems are usually kind of a little bit longer. Like I wasn't really prepared for the short answer. Like for the short, I mean, like for the 15 questions. You know what I mean? Like they were just kind of like, oh, okay. Like they didn't need as much work, I guess.
Yeah.
And it's like the longer ones took me a while.
Okay.
Yeah.
So we have that. The one that I'm kind of like, where am I trying to go? I honestly have more of an issue with number theory. Because I mean, I get the idea of probability, but like I feel like if we go into any more detail on probability, like Bayes' theorem and stuff like that, I'm just going to start to get confused. And then number theory is like a fun issue for me.
Do you have any example problems you want to go through or anything? Like, did you get the homework for that?
Yeah, no, I have the homework right here. But I would have to say, like, you know, if we did something with Bayes' theorem, that would be fantastic.
Actually, what you're saying about Bayes' theorem and me like multiplying it, I was actually still right though, because the thing about like if it's equal to multiplication if they're independent, no, if it's not equal to the multiplication if they're dependent, but it is actually.
Mhm.
Yeah, because the intersection of E and F, the probability of that is equal to E times F if they are dependent. Let me just check right now. Sure. I have this open.
Harold does bring up a good point. We won't get into it if we don't have a structure. So
Yeah.
what I think we should do is we should work backwards. Start with induction. Do a problem, and then like move backwards.
Oh, that's true.
To get to like pigeonhole, which is like the first thing that we have.
Okay.
So does anybody have any questions on induction?
I don't.
1 second.
No.
The homework. Can we do? 1 second. Number. What number was it? It's part B of a number. Hold on.
Part B of a number. Gotcha.
Part.
Oh, my mouse.
Okay, I think it's number 3, part 2.
Number 3, part 2.
I think so.
I mean.
Yeah, because I could prove part 1, but I forgot what I did for part 2, and I felt like I wasn't getting the right answer.
Let me see.
Oh wait, the answers were posted, weren't they? Yeah, they were.
They are posted, but you know it's very good.
It's better to do it without it and see if we did it right. Yeah.
So let's see. For assignment 8, correct?
Yes.
Okay. Let's see if I can pull that up. Yeah, my mouse just like died on me. That's okay. I have another one. BRB. Can somebody pull that up on their screen?
1 second, I got it. Number 8. Okay.
Ow.
Number 4. Okay.
Okay. And on. Oh, it's so much better. Okay. By the way, guys, never buy a $12 mouse from Best Buy.
Okay.
Not worth it.
Mono price, man.
Okay. So, we have it up. Let's see.
Yeah, I have it up right now.
Okay, this problem has two parts. Maybe. Okay, this one was fun. Okay. So, for this one, you have to prove 1 before you get to 2. So, prove that a product is a rational number and an irrational. And prove that the product of a rational number and an irrational number is irrational.
Mm.
First step, like, do you kind of like agree with that statement? Do you kind of like see like?
I can see why that's true.
Okay, so now we kind of have to prove it like formally. So let me go and let me show you how I did it.
I just copied what he wrote for assignment 8.
Wait, what did he write?
Let's say A is rational, and B is rational, and B is irrational, then C is rational, then that means C is equal to A times B, which is also rational. And that means C divides A, which is true, and that means C divides B, or no, B is equal to C divided by A, and that can't be true because a rational and irrational number cannot be written as an integer divided by another integer, or a number divided by a number.
You have a point. That's kind of what I put down. So, for instance, for mine, I have that, right? So basically, I put an irrational number times an A divided by B number, which is the definition of rational, implies, and this is a proof by contradiction, by the way, implies A to the I over B, which makes no sense because it can't equal A over B by definition of both, right? So that's our contradiction. So now, because it's a contradiction, I prove that it happened, right?
Yeah.
So therefore, now I have my kind of like my lemma, as it were, to go ahead and prove the second point. The second point is let A be an irrational number where A squared is a rational number. So my thought process was, okay, is there any point in time where that that exists for a certain set? And I think what I was thinking of was root 2, right?
Yeah,
Root 2 to the 1.
You can prove that if you multiply a rational number by an irrational number, that's going to be irrational based on your previous proof from the previous problem. And then if you multiply that, and if you multiply the irrational number by itself, when you get to a to the 4th, it's going to be rational again. But the thing is, the problem doesn't ask you to prove that any of them beyond a squared is rational. It only asks you to prove that the odd ones are irrational. And you can just say that, I'm proving that all of them are irrational. You multiply rational by irrational, you get irrational. If you multiply, I don't have to prove that the rational ones are even. I'm just proving that all of them are odd and that all of them are irrational. And because of that, all of the odd ones are irrational since they are a subset.
Okay.
Oh shit! I just realized I'm not talking through my headset. I was talking through my webcam, so I was walking around. Did you catch what I was saying?
I kind of lost you halfway there.
Okay, so let me just say it again quickly. You multiply. You don't have to prove that the even ones are rational. You only have to prove that the odd ones are going to be irrational. And you know that from your previous problem, if you multiply irrational by irrational, you get irrational. So that means when you do 8 times, that means that, you know, all of the ones, a lot of the future ones are irrational, and it doesn't matter if, you know, the even ones are rational or irrational, because you prove that all of them are going to be irrational, and the odd integers are a subset of that.
True. So in the homework we had to prove it, you know, using induction, right? So based on that, you know, that premise, what I did is, like, you know, base case. A to the 1 is irrational as defined.
Yeah, I did the same thing. And then AK is irrational for all odd integers k greater than 1. They have to prove AK plus 1. And then AK plus 1 is equal to AK times A, and premise A is irrational. And then if AK is irrational, AK times A will be irrational.
Mm-hmm.
Yeah.
I actually put my inductive step to be AK plus 2.
Oh,
Right.
Well, still, that's,
That's legit. Erwin said so.
Yeah.
So not that he can't be wrong, but I mean...
Yeah, actually, no,
He's a
yours
graduate
makes sense
student,
because you're
so-
multiple, because we already said that our hypothesis is that AK is irrational. And AK plus 2 is A squared because you're multiplying irrational by rational.
Really quick question. When he gives us an induction problem, like, he would specify whether or not we would have to use strong or weak induction, right? So,
Um,
different.
Maybe, but
Honestly, like, the only cases he's given us strong induction are for the stamp problems. I mean,
well, I think like the only thing like you really have to use the only difference really between strong induction and normal induction is that strong induction you just have to use multiple base cases.
yes, I mean, the weak induction is more like math.
No, I think they're about the same. Just you know that at a point with strong induction your thing will just loop and you only need to prove for a certain amount of base cases.
Wait, hold on. Can we get back to the original question? I forgot who asked the question in the first place.
Oh, it was me.
Wait, who was that?
Fosley.
Bosley.
Yeah.
All right, grab your angels. No. Wow, you didn't get that joke. I feel really bad.
Oh, no, I didn't.
All right.
It's okay. It's okay.
What was it in reference to?
I'm like, come on, Charlie's Angels reference. All right.
Oh, Bosley? Oh, no, it's with an F, though.
Oh.
I've gotten that before, though, so it's okay.
So, Bosley,
Yes.
do you understand kind of like what's going on? Like,
After looking at this, I do. Like, cause I did part A, and then when I tried doing part B, I don't think I did it right. But I understood this part, but I think after looking at it, I get this second part too.
okay, cool.
Yeah.
Like, do you have any other additional questions about that?
This is the only induction one that gave me problems.
Okay, cool. So now back to the strong induction part, which I actually have a theory on this. The strong induction you only have to see strong induction when you're dealing with a situation with stamps. So
I don't think he's given us any other strong induction problems. So I'm assuming. See, the only thing is he said there would be definitely an induction question for one of the big three. But if he I'm assuming I don't know. It just seems like if he were to give us one strong induction, it doesn't take that long to actually answer. You know what I mean?
Yeah.
I feel like it's not big enough to be one of the big three. But he said induction is probably definitely going to be one of those. So I'm assuming that he would have multiple parts, and maybe we have to prove the same thing, strong induction and weak induction, maybe something like that. I don't know.
No, because strong induction, all strong induction is induction, but with multiple base cases.
Yeah, with cases, exactly.
Essentially, what you're doing is you're presenting multiple base cases to the point where you can just say, "Oh, this
it works for everything.
I happen to have that I already know is true. I can just put that into my equation, and I'm done."
Yeah. And
the Fibonacci sequence is also
for the
strong induction.
Oh, sorry.
That's okay. The Fibonacci sequence is also strong induction.
Oh yeah, true. No, but for the whole base cases for the strong induction, somebody in my class said for the stamps, you can either do if he gives you oh, you have to make 20 cent postage with 3 cent stamps, 4 cent stamps, and whatever. like apparently like the lowest number of like the 3-cent stamp, like you can do 3 base cases or like the highest number of stamps for it to be correct.
Yeah.
Yeah.
Yeah. That's essentially what I did for the problem. I was like, okay, well, what do I need to prove above my original base case in order to just place that 3-cent stamp that I already know is true and put it in there? So it would be like k plus 3 is what I ended up getting, I think.
Yeah.
So there we go. All right. Now, any other questions related to induction or strong induction?
I don't think so.
I'm probably going to go get some rest, but good luck to you guys. I don't know how you guys can stay up so late. Like, for the last review, like, I couldn't stay on for, like, you guys had made it, like, 4 hours. Like, I don't know how you do it.
I didn't stay for the whole thing.
Yeah, I just can't, like, concentrate that long either. I need sleep.
Yeah, I feel you.
Good luck to you guys.
Yeah, good luck to you. Good luck on the test.
Oh, yeah, we'll see how that goes.
You'll do great. I believe in you.
We believe. You can. By the way, you can also watch this on YouTube.
Yeah, I'm definitely gonna watch it after. Like, I'm gonna like see where I left off.
Yeah, it's lots of fun to see my face on YouTube
All the time.
in another class, and I'm like, oh, it's me.
Yeah. All right, see you guys.
All right, bye.
Okay, so real quick, I do have to answer a question. Trey McCoy is having a problem with Vark's solution to the probability.
I think he left.
Did he really?
It said left
Yeah.
group chat.
Oh, well, punk. All right. No. No, but I think he does prove a point because they all have to add up to 1, right? Whenever you're doing a probability problem.
Yeah, so if you roll the dice and it's without replacement, then you can essentially consider that side being removed from the die.
Mm-hmm. Yeah. So
it should be out of 5.
Yeah. When I was trying to explain it to him, it's like every iteration, it like in this case, it gets removed by 1, right?
Mhm.
So right here we have 1/2, 1/2, or 3/6, 3/6, and then the second one we have 2/6 odd because we removed 1, and then 3/6.
But that only gives us 5 out of 6 instead of 1.
Exactly, but we can
Yeah.
remove that 1 because we're getting rid of it, so it comes out to 5/5.
Yeah.
Which adds up to 1. I just wanted to clear that up in case anybody was kind of like confused as to what was going on. But anyway, so let's go back to assignment 7 or the
Number theory, right?
Yeah. Oh,
Yeah.
Lots of fun number theory. Okay. There's going to be a mod problem on here on the test, and I have no idea how to do it. If I'm going to be honest, like I'm very confused as to what's
Like
going on.
mods in general or mod inverse?
I understand the idea of mod, but I think I'm having a problem, like, putting the equations in my head and then trying to map them. Because last study group with Rachel, I was kind of like looking at it, and I was just like, yeah, that kind of makes sense when you write it down, but I don't think I can do it like by myself. Like,
I think for all the mod problems, as long as you know the 3 definitions, which I have on my screen on the left if you can see it, I think as long as you know those, you should be able to solve them.
Yeah, A is equivalent to B mod M. That means both of them are equal to the same when mod M equals A minus B. M can divide A minus B. A is equivalent to B mod M equals, yeah, of course.
those
mod
are the
M equals, there exists a case such C such that A equals B plus K. Yeah, that makes sense, because A is equal to B plus, because, like, it's going to loop around. Like, if you just move it that many times, it's eventually going to loop around.
That's kind of like how mod works, essentially.
Yeah, I've done it a lot in programming.
Yeah, I'm doing it in my my computer security course. Like, I'm always having a question with mod. I'm like, this is fun. What was I gonna say? So, if it's okay with you guys, can we do a question with that in there? Like an assignment 7 question. Let's do. Let's see. So I'll be honest, I think this was the worst assignment that I got this round.
How did you do?
I think I got a 50.
Oh, wow.
Yeah. It was either it was this one or the one before it. Like the one before it, I was actually surprised because it was right after spring break, and I didn't do very well, and I knew it, but I got like 74. So I was kind of like odd. But this one I think I got like a 50 on.
Okay.
So I know how to do problem 3. Problem 3 was not too bad. Let's do problem 1B.
On assignment 7?
Yeah, on assignment 7.
Okay. Pull it up. For B. That's actually pretty easy. So for all how did I do it again? You do n divides m. That's given. M is equal to n times p, and and A is equivalent to B mod m. We can say that A is equivalent to B mod n times p, and then n times p divides A minus b. N times p is equal to A minus, or n times p divides A minus b. N times p equals, I mean that's using the rule of like mods and stuff. N times p equals
Bart,
A minus n times p. What?
Could you do me a huge favor and write it down, like on the whiteboard?
I'll just hold on. Let me.
That would be super awesome.
I'll just copy paste it the lazy way. Here we go. There we go. Let me make it bigger. There we go.
Okay, so we have prove or disprove, and so we have n is greater than 2, m is greater, okay. N divides m, that's given. Alright, so m equals n times some p for some p of z, and then we have ab mod m, ab mod np. Wait.
That's a really weird way.
So we have AB mod NP, NP, okay. Then you have MP, which is M, divides A minus B, which is the definition of modular congruence. And then we have NP equals...
Let me just show you what, look at, just
Hold on.
This one's, I think, is easier. Can you see here? 1D?
Yeah, I can see
That's
it.
yeah, that's probably No, I can't.
This is a lot easier.
Let me see. Hold on. Given that A is m speed, and we know A equals B plus mk, and that m equals. Can you not highlight it? I can't really read it. Okay. Then we know A equals B plus mk, and that m equals nc. I find my way easier, but different ways, I guess.
Okay. Mine's like
So,
3
like, programmers
sentences.
arguing, my code's better than yours.
Hey, I mean, like, if that's how he thinks, go for it, but that's a lot of not words, and I like math, but not that much.
I'm not good with words.
I mean, like, we're saying, hey, we know this, right? And we know that this thing is true. So I declare all my variables, and then I'm like, hey, because I know that this is a mod, I can use this definition by this theorem.
Oh, yeah. Oh, I see what you're doing. You do, like, it's equal to nck, and then you take out the ck, and then it's just mod n.
Exactly.
That's how
So
it works.
it's like just 2 substitutions, then I'm done. I just explain it with words, so I'm not pulling stuff out of, thin air.
Yeah.
That makes sense. I like both of them. They're equally fantastic.
His scares me a little bit more. It's like, I don't know if I could do that
I'm
on the
used to
fly.
doing proof and steps, so...
Hmm.
Go for it. No, once he showed us the informal proof, I'm like, let's do it. I like informal proofs.
I think he did the same thing. It was just like, you know what, informal proofs all the way. That's how
Exactly.
I proved it. Harold says he proved it the same way as Madeline.
Oh, I love you, Harold. Thank you. Makes me feel validated.
We got 2 for the informal. Sorry, Vark.
That's fine.
Outvoted.
Outvoted. Okay. Well, that actually does make a lot of sense. I think what I need to do is just, work out some problems and then kind of like figure it out and figure out the best way that I can do it. But as long as you have those three definitions, then you'll be able to solve
all of them. Yeah.
You really only need 2 too. Like, let me show you. Once he showed us this, I was so elated. So we know that where's my drawing tool? So we know that A is congruent to B mod M, right?
Mm-hmm.
And so we have to memorize 2 different definitions. Well, one of them is if we have B is congruent to A mod M, which is easy to remember because you just have those 2. Well, the next one that's fun to remember is A minus B. This one you can use to derive the other one. If you have this one, then you can derive the other one, Can I scroll up? Yes. So we can have it, like, the definition of division, right? A minus B is equal to mk. For some k, that's an integer of z.
Mm-hmm.
And then all you have to do is move this b over. So it's A is equal to mk plus b. Oh, hey, look, that's our 3rd definition we have to memorize, only now I don't have to memorize it. So.
All right.
And then this one's fun because it's in the same order as these guys, right?
Yeah.
Like, this order is the same as this order, so...
So as long as you know the mod, like the first part, and then you know the definition of divisibility, you can derive the rest of it, pretty much.
Exactly. You can derive this one. You don't have to memorize it, which is fantastic. So...
I love memorizing things.
I hate memorizing stuff.
Okay. All right. So that's actually pretty good. Does anybody else have any questions about assignment 7 and number theory?
Kind of good. I don't know. Like, I went through all of it with a friend of mine earlier today, and I feel really prepared, which kind of scares me.
I feel confidence. But I'm not sure. Mm-hmm. Okay. Then, if you like, we can move on. That's not a problem.
Okay.
Because, probability is a thing.
It is a thing.
And don't get me wrong, probability is, like, for me, probability is like counting because it's just...
Yeah, same.
It's kind of like, sometimes, like, for instance, like, I'm pretty sure I got a lot of this pretty wrong. But then again, I don't know I'm not entirely sure what I did wrong because I felt like my logic in my head like made sense, but it actually didn't.
For assignment 6?
Yeah. Like, for instance,
what did you do?
Well, here's how I would read it, right? Like, problem 1, you have 6 chess pieces, right? The set containing all unique pieces in the game of chess. Suppose you generate A set R randomly by setting 4 elements from C without replacement, right?
Yeah.
Now I was just like, okay, well that makes sense. What's the probability of the queen that's an element of R? Okay, so now I'm kind of like, all right, so out of these 6 pieces, right, we have, we take out 4 of them at random, right?
Yeah.
And like my first like instinct is to say, okay, we have to take 4 of them and then like do kind of like a combination problem, right? Yeah. Where like we have to choose each 4, like, and then we have the total number, and that's our set, or that's our S on the bottom, right? Which makes sense because like I'm looking at the answers, right? And it's 6 choose 4, okay, which comes out to 15.
Yeah.
Right. Okay, cool, good. And then you have the probability that the probability that the queen is an element of R. Okay, so out of those 15 times that we select, what's the probability of the queen? And then at that point, I'm just kind of lost because I don't know. It's just like I draw a blank.
So let's look at that this way. So go, nope, wrong one. So, I'm gonna draw. So we have 6. We have to choose what, 4? We have to choose 4 elements, right? 1,
Yep.
2, 3, 4. And before we could choose whatever we wanted. You know, we could pick out of, we could pick 6 different. No, because without replacements, we could choose 6, 5, 4, 3 different pieces, and happy things are happy. But now we can't do that because we know that the queen's going to be here. So there's one way we're going to do one thing. And so now we no longer have 6 elements to choose from, right? We have 5 elements left. And we're not choosing 4 anymore. We're only choosing 3, right? So it's 5 choose 3.
Okay.
Times 1. Or there's no...
Times 1, which is the same thing.
And then that would be over 6 choose 4.
Okay.
Because this is total possibilities versus just those with the queen.
Okay. So this is another question that I had in the study group yesterday, right? So the problem is that you have a deck of 52 cards.
Okay.
Right?
Yeah.
And in this deck of 52 cards, what is the probability that you will get 4 of a kind?
Okay. So you'd have to. So how many do we choose?
Well, your first thing you choose 1 out of 52. So you choose 52 cards. So there are 52.
But I mean, like, are we? Sorry. Are we drawing 4 cards or 5 cards or what? Does that make a difference?
5-card draw. What's the probability that you get 4 of a kind? Where is the answer in this book? Oh, the book that I didn't buy. Okay, never mind.
So let's say you. So actually, I think I know what to do here. So I'm gonna draw it on my screen. Hold on. So you draw a card. That's Let me make this invisible. You draw a card. That's You already have 1. Now there are 51 more cards in the deck. So let's say the one you draw. There are 4 of each kind of card. Wait on. Not. Yeah, there's 4 of each kind of card. So let's say you have 13 different kinds of cards you can draw. There are 50. Shit. You have a 1/4 chance of drawing each kind of card except for the one that you just drew. Or no, 1/13. You have a 1/13 chance of drawing each kind of card except for the one you just drew. So, which would be, you would have, shit. I can't think. You have, okay, 1/4/13. You have a 3/52nd chance of, drawing a card after. The rest you have 1/13. So then you have that means you can either draw these 3 out of 52. Wait, hold on, shit. These 3 out of 52, you can draw. Let me do times 12.
So where's the what's the?
So that means 48 out of 52 plus 3 out of 52. You have a 3 out of 52 chance of drawing it. Then you have another shit. Then you have 2 cards. Shit. Okay.
So Vark, real quick.
No, I know what you do. You take all the sample spaces where you have Are you looking for 4 of the same kind of suit or 4 of the same kind of number?
4 of the same kind of number.
Okay, so you look at all the sets you have that do this 2, 2, 2, 2, 3, 3, 3, 3, and you have 13 of these sets. And then you look at the sets that don't have it. You have 52 choose. No, you do a you do permutation. There are 13 combinations, 13 to the 4th power.
No. I'm sorry, you're off in the bushes. Okay, so.
I find it's
Order
always
doesn't-
easy to find cardinality of E and S for basically all of these. I think Rachel has a point, but the point that I have with this problem is that I have a really hard time finding E and then S when it's just written out for me. Because I don't know, I just wish it was just presented to me in math.
Here you go. Look at this. Oh, Rachel, go ahead. You do it.
Ooh.
Well, I was just gonna say with the card problems, like when you're dealing with a kind, I'm trying to think of ways to generalize it for you so that it's easier to kind of generalize. Oh, okay, it's a card problem. So if you're dealing with kinds, it's gonna be if you're choosing one kind, that's 13 choose one. It's just 13 kinds.
Yeah, I get it. You do 52 choose 4 because you're choosing 4 from 52.
Choose 5. He said we were
Yeah,
choosing 5.
Yeah,
Oh shit! You're right. You're right. But how do we have 5 of a kind? There aren't. That would be 0 because
No.
there's only 4 of each kind in the deck.
We
No, you're
choose 5.
We're looking for 4 of a kind. We're drawing 5 cards.
Oh, okay. 52
Yeah, your
choose
S is
5,
52 choose 5.
and then 52. This is your sample space, which would be 47, 5, shade 2, shade 1, 10.
It's a huge number.
Yeah.
49. And then you take out 4, 3, 2. You take out 8, and you take out 3. Take out 24, 2. This is your sample space. Now basically what you do after that is you look for the sets that have a card 2, then you
Hey,
look
buddy.
for, what? Yeah?
So, how many successes could you possibly have total?
How many successes? I'm not sure. I can't think right now.
So, how many numbers, right? It goes from ace to king, right? There's 13
it goes from ace to
cards.
king. That's basically 1 to 13.
Right. So you can have how many successes if you draw 4 of a kind correctly?
You can have.
You could draw all aces. You can draw all 2s.
Yeah. But no, you can't draw all 2s. There's going to be 1 extra.
Yeah, but that doesn't matter.
Okay.
We don't care. So you can have 13 successes, right? Because if
Yeah.
you draw all of the cards, you have 13 4 pairs of a kind, right?
Yeah.
So whatever our E is, our success will be the 13, our number of successes. That's the probability we have. Over how many possible combinations are there, though? That's this huge number you're trying to calculate.
Yeah, I know. That's the sample space.
Right. So it'll be
13
13.
Divided by this.
Mm-hmm. All
Yeah.
that. And that'll be the probability.
It's not
Right?
just 13, though.
Yeah, that's what I was saying. Because you have to count for the extra card as another set of sets. Because okay. Let me think for a moment.
Yeah, exactly. So basically, you have to account for there's 48 cards remaining after you've got the 4 of that one kind. And so you have to choose one of those 48.
Yeah, so you have to multiply
I understand.
13 by 48. Actually,
Yeah.
that's what I was thinking. There are 48 cards remaining, so you multiply by the remaining 48. Oh man, I hope I don't lose this stuff during the test, before the test happens, or maybe I'm just sleepy, I don't know.
Ah! Sorry.
So why do you multiply by 48?
Because there are 48 cards. After you choose the 13 that are the same, there are going to be 48 left, and you're drawing 5.
You're drawing one more out of the 48 left.
Yeah, so there are 48 total cards you can do.
Aren't we looking for the probability of success, though, of pulling out a 4 of a kind?
But you're having, like, you could have 4 aces plus a 2, 4 aces plus a 3, 4 aces plus a 4. You get it? So, like, the 13 there is for your 4 of a kind, but you are getting a 5th card, and so having, like, in this situation, having 4 aces and a 2 as your 5th card is different than having 4 aces and a 3 as your 5th card, etc.
Oh, so they want all the they want all the combinations of hands that we could have that give us a 4 of a kind.
Yeah.
Oh, okay. That would make sense. Never mind. Okay. I'm like, because the probability won't depend on, like, if we just want the probability of success, it doesn't matter how many, that we need to have 5 cards. But if we want the number of hands, then suddenly that makes
Right, because all of these deal with, like, the realities. The reality is that you have 5 cards, just like when you're thinking about whether order matters and doesn't and all that. Like, you have to think of it framed in the reality of I've done this thing first and this one second. That's why, like, rolling a 6 and then a 5 is different than rolling a 5 and a 6, even though they both add up to 11. Like,
You have the total probability is 1 out of 4165, but he's probably not going to ask you to calculate that on the test.
No calculators, so that'd be kind
No,
of
not even like solve it. I mean, just do like the basic form of 13 times 48 divided by 52, choose 5.
Yeah.
Yeah, as long as you put the choose into factorials, you can leave them in factorials. Like, that's been the standard.
Yeah.
Okay.
That makes a little bit more sense.
Let's do another one.
Do you know the probability?
Yeah.
Okay. Let's do.
I found a gap in my knowledge. Let's go.
There's a gap.
I must fill this gap before the exam tomorrow.
Okay, what about C and D of the same problem 1, where you have K union Q and then K intersection Q?
So C and D of problem 1?
Yeah.
Oh, for assignment 6, though.
Yes.
Okay.
So for this one, he's using the exclusion principle for probability.
Yeah.
So in that case, part A. Okay. So your sample space is 15 because that's what we figured out. We're pulling 4 each time. It's always going to be 15.
Yeah.
Okay. And so our queen and king, let K be the event that queen is an element of R and Q be the event that the queen is an element of R. What is the event, or what is the probability of kings and queens in your graph? Right. So if we're doing the inclusion-exclusion principle, we would do P. It's not writing today. P of K union Q is equal to P of K plus P of Q minus P K intersection Q. Right. So from part A, we have from part A we already have 2/3. That was the answer because we did 5 choose 3 over 15, which comes out to 2/3, 10 to the 15. So we have that. And then from the king, we could do the same thing because it's just, one other grab. So it's also going to be 2/3. So we have P of K and P of Q. It's 2/3 plus 2/3. And then we do minus P of K intersection Q. And I believe, if I'm not mistaken, we just multiply those two values together. I feel like I'm wrong, but
What did you have for it?
4/9? No, that doesn't make any sense.
No.
No.
Do the same thing we did last time. You know, you can't pick the queen, so that probability is 1. And you can't pick the king, so that probability is 1. So how many do you have left to draw from?
2.
You have to draw 2. And then how many do you have left to draw from? Not 6, but rather
4.
4. So it's 4 choose 2.
4 choose 2. Okay, so 4 choose 2. 4 choose 2 is equal to 6. Wait, 4 equals 2 minus. Oh shit, I'm drawing like 4 factorial. 2, 6 over 15.
Yeah.
Okay, so now I have 6 over 15, which is, okay, so that's 10 plus 10 minus 6. 20 minus 6 is 14 fifteenths. Okay. That makes, okay. Oh, that's fancy.
Mm-hmm.
Okay. And then, you know, we, like for D, we've already solved that part from, you know, from C, so we could just add that in there. So it's 4 choose 2.
Yep.
And then that's it. Okay. Cool. That
Beautiful
makes,
work.
huh?
Beautiful work.
Thank you.
What I did is for like determining the king intersection queen. What I did for determining king intersection queen is I just looked at the sets that I said like, okay, the king and queen are already in here, but what are the rest of the pieces? And it was gonna be two of them out of 4 possible ones, so I just did 4 choose 2 and then divided that by the sample space. And for the other one, I just looked at sets that didn't have king or queen, the complement of that, and I divided, or I did the complement of the complement.
Yeah. Okay.
Oh, okay. Yeah, that's actually his alternate solution, right?
I think so.
I always do the alternate solution without realizing it.
That's good. It means you're thinking mathematically.
Yeah.
That is fantastic. Does anybody have any other questions about, you know, probability? I think. Yeah, there's that 20% chance one.
I have to go, guys.
I should probably get going also. It's getting kind of late. I need to like cool down.
I mean,
What is this? No, we're doing this all night. What are you
it's
talking
only 11 o'clock, but I have to go do some stuff.
about?
And I gotta take a shower and then do the dishes.
TMI.
Be well rested. Get a lot of sleep, guys.
Yeah.
I got a class at 9, but I'm probably
Oh, me too. Wait, what class do you have at 9?
CDA, computer organization.
Oh, with Sir Angel? Me too. In business administration,
I'm
right?
taking that over the summer.
Good luck. It's an impossible.
I don't even know what she's been teaching for the past 2 classes.
Dude, yeah, it's the same with me. Like, I have no idea.
Yeah.
No idea what's going on.
Alright, well, I'll talk to you guys later.
All right, see you.
Yep.
Harold, I already have groups, but essentially it's writing. This is totally unrelated to discrete, but it's essentially writing the data path in C. I feel like the project is not as hard as people make it out to be, but then I don't know.
I have no idea.
Yeah, CDA is a thing.
I'm taking it in the fall, so.
All right. So, can we do one that kind of covers Bayes' theorem? Because like, and I feel like I kind of need one that's a little bit easier than the Game of Thrones references, because I get super confused with Game of Thrones references.
I hate that one. It's like as soon as I see, and then we have Peter, and I'm like, oh no, please no.
It's like someone's gonna die. Does it really matter? You're gonna ruin the fun of Game of Thrones.
Yes,
The
because
probability of somebody dying.
like 100%, everyone's gonna die. Problem solved.
Yeah. The only time where people don't die is when the author is dead.
Yeah. Then he stops writing books.
Yeah. Yeah. Do we have a decent one for Bayes' theorem?
There's probably one he gave us in class. Or I guess technically we could do any of the given probabilities for Bayes' theorem. I mean, it's not like it's not impossible to do.
There's one of them on the practice problems, and then like one of the practice problems is like do it and find a different thing. So there was the one with the medicine, which was actually pretty cool, and then there was another one like to find the opposite of whatever he found.
Let's see. Which one was that? Which practice problem one was that?
Yeah, let me pull it up.
Vivian is doing some serious typing. Or clicking. I haven't been to class in a month. Harold, I'm going to be honest, I've been to the class, but I haven't been there in a month.
I'm trying to decide whether to take it in the summer or the fall. Like, is it really bad or something? Like, what's up with that class?
It's not bad, it's just really dry.
Okay.
It's like, here's the thing, right? You know how Szumlanski knows that, like, discrete is very, like, it's just in your face, and this is what you have to learn, and if you don't know it, then you can't take the foundation exam. So he tries to make it as entertaining as possible by injecting muffins into everything.
Right.
I love the muffins.
Yes.
I wrote, okay, so I had a test in physics, and that's the class that's right before discrete, so I got to class early instead of, like, right on time. And so I was walking by Joffrey's, and I found they had muffins, and I'm like, I'm going to buy him a muffin. And I bought the muffin, and I put the muffin on the desk with a note saying, I am the comestible muffin. Please stop mocking me and my brethren. Sincerely, the comestible muffin. And I got no response. I have no idea what he thought of that, or if he's seen it, or anything.
So last semester, when I took this class in with Drew,
Sorry.
it's okay. Basically, he told us the story about how he got like a bunch of muffins. I don't know if he told the same story, but like he had like a whole tray of muffins that was delivered by one of the students, and he wouldn't eat the muffins. He would let his TAs eat the muffins.
He thinks he would mock you or something.
Harold has voice. Yay!
Yay.
Now we just need Jones to talk and Vivian to talk.
No, I'm sorry, I'm eating actually the whole entire time, so.
Oh, it's okay.
Yeah.
Was it muffins?
No.
Failed us. You're supposed to eat muffins when you're doing discrete. It's like
yeah,
a
it's
rule.
gotta be muffins. If you eat muffins during discrete hangout sessions, then Szumlanski and maybe even Fontaine will come and talk to us.
I don't think so, but.
I don't think so. I think it's just like.
Probability part 3 has the test one, like test negative, test positive one, and then probability part 1 has the urn and the balls and the motors. So all of those. The drug one was actually kind of cool, just the result that you get.
Where's the drug one?
Probability 3-3, and it's in the notes.
Probability 3 in the notes. Okay, hold on. Let me pull that up real quick. Is the very first one? Suppose one person in 100,000 has a particularly rare disease.
Right.
Okay, let's say which is very accurately does not test. It says correct 99% of the time when given to a person selected at random with a disease. It is correct 99.5% of the time when given to a person selected at random who does not have the disease. There's a probability that person tests positive with this test actually has the disease. Okay.
Right. So he solves that one there, and at the bottom he's like, exercise for you at home. What's the probability of someone who tests negative doesn't actually have it? And so I did that one, and it was actually really cool.
Okay. So and that's on the very bottom.
Yeah.
Everywhere. Okay. All right. So let's go with. Can we use the same events? Is that what we're doing, or do we have to use?
No, you'll have to use that E is the person tests negative, and F is they do not have it.
Okay, so E test negative, and then F does not have disease. Disease. Okay. So is it asking the same question? So like in the top, it's like, so the question is asking for P of F bar E.
P of F given E. Yeah, like that's basically what they're asking in the first one, and then I just now set up what we're solving to be the same thing. We're looking for P of F given E. So the P of F, like, what is the odds the person does not have the disease given that they tested negative?
So P of F given E is equal to P of E given F, P of F, all over P of E F, P of F, plus P of E F's complement, P of F's complement. Okay.
And I learned when I was studying all of these, like, you can actually solve these multiple ways. Like, you could use Bayes' theorem, or you can use, like, intersections and different definitions there. But sometimes, depending on how they're set up, it's a lot easier to do one versus the other. And this one is really easy because they basically give you P of E given F, and and then you can just do subtraction to find the E given not F. And so you would want to use Bayes' theorem in this, just like you did in the first one.
Okay.
Yeah.
So let's let me try to figure it out.
Yeah.
So we're given that it is correct 99% of the time. So, okay, hold on.
Wait, yeah, reread it.
Yeah. Suppose one person in 100,000 has a particularly rare disease.
Okay, so what is that piece of information?
One person in 100,000 has a disease. So that would mean that it would be that would be F complement.
Yeah.
Oh, well, fine. All right, so P of F complement equals 1 of 100,000. Okay. For which there's a fairly accurate diagnostic test. This test is correct 99% of the time. So that means that the test negative.
Well, read that whole sentence.
When given to a person selected at random who has the disease. Okay, so that is who actually has the disease. That's F complement given E, right? Or
What's E?
E is test negative. Okay, so E complement.
Yeah, F complement, E complement. It's F complement, E complement, and we don't need that.
Yeah, no. I just want to make sure that I'm understanding
Yeah.
words to variables, I guess.
Yep.
All right, so we don't need that. So that's a useless piece of information. It is correct, however, 99.5% of the time given to a person selected at random who does not have the disease. So that is F given E complement.
Read it again.
Right. It is correct 99.5% of the time when given to a person selected at random who does not have the disease.
Okay, and what's E and what's F?
E is test negative. F is does not have disease. So that's F given E complement.
No.
No.
So it's saying that this might be, I don't know if I'm going to be saying it too plainly or not, but when it's correct 99.5% of the time when given to someone who doesn't have it. So when somebody doesn't have it, they test negative 99.5% of the time.
Okay. So in that case, it's and I'm really drawing a blank. Okay, so it's correct. So it's selected around who tests negative. Okay, so that is E.
Probability of
Oh
E.
yeah. Okay. So it's correct. Meaning that it tests negative.
Yeah.
So that's E given F.
Yeah.
Okay. Cool. So that means that it's 99.5%. Okay. So E given F is 99.5%. Awesome. So in that case, we have P of E given F at 0.995. Yeah. Okay. So now we have P of F is, if I think I'm doing this right, it's 1 minus 1 over 100,000.
Yep.
Yeah. Okay. 1 minus 1 over 100,000.
Mm-hmm.
Okay. And then we have, okay, so we have P of F here, P of F complement, P of E of F, P of E of F. And the other thing that we're missing is P of E o given F's complement.
Yeah. So the probability that they test negative, given that they have the disease.
They test negative given that they have the disease. When given the person selected at random hits. So
Oh, this is interesting. So
if this is correct 99% of the time when given a person selected at random who has the disease. So that is test positive. Wait. So if that's the complement. Wait, am I overthinking this? What am I doing?
You're looking for E given F complement now?
Yeah.
So that's they test negative and they do have the disease.
They test negative and they do have the disease. So would that be would that
no, wait,
be
the useless piece of information from before, couldn't we get it from there? The test is correct 99% of the time when given to a person selected at random who has the disease. Well, we know the person has the disease, but the person tested negative. So we couldn't use that piece of information? Yeah, because that's probability that so 99% of the time, that's the probability of E complement F complement, right?
E complement F complement is the 99%. Yeah.
Yeah. E complement F complement. So then if we just want E F complement, right, we just take this and we subtract it from 1. So it would be 1%. The probability of E given F complement is 0.01, right?
I was thinking it was the other one, but now I have to like double because I was thinking it was the 95 or the 1 minus 95 because they do they do have it and they test negative.
Because the test is correct 99% of the time when given to a person selected at random who has the disease. So given that the test is correct, given that the test is positive, so probability of E complement, given that they have the disease F complement, is equal to 0.99. Well, Szumlanski has it in his notes. He takes probability of E given F complement and he subtracts 1 from that, and he gets the first variable on the given changes from a regular to a not, you know?
Yeah.
So I would imagine it'd be the same since we want E given F complement and we have E complement given F complement. We just have to take that value and subtract it from 1, you know?
Yeah, we do. I just, I did subtract the wrong value because I subtracted the 95% instead of the 99%.
You're fine. It's okay.
But yeah, you're right. It is the 99% that we need to subtract from.
Ooh, so P of E given F complement is equal to 1 minus 0.995.
No.
No, I'm sorry, 99.
999.
99.
Yeah.
99. 1 minus 99%.
Yeah.
Yeah.
Okay.
And you multiply that by the F complement we found at the beginning.
Yes, correct. So we have all the values. All we have to do is just plug them in and we're done.
Yeah, calculator math. But since there's no calculators on the exam, we're done here.
Yeah. But the cool thing is when you work it out, it's basically like it's 99.99999%. So essentially, like what this is it's a rule-out test because like the it telling you that you have it was pretty crappy like probability, but it's pretty accurate when it says you don't. So it's like a rule-out test, and I thought that was kind of cool that like we can work it both ways and see that.
Oh yeah, because it's safer that way. So if you don't have it, you're more likely to not have it. But if it says you do have it, then you still might not have it. And I like that. I like that kind of exam odds better. You know.
Yeah.
That's pretty cool.
Still a chance.
I can dig it. All right, that is pretty sweet. Any other questions with probability? I think we hit the main topics with probability, right?
Yeah.
I'm not doing any flower ones. Those are crazy.
Yeah. No mystical snowflake creatures.
The garden of wonderful knowledge. Don't eat the black leaves. Mm. Yeah, I'm eating black leaves all day. Alright, so that just leaves assignment 5, which is pigeonhole principle and what else? What was it doing here? Oh! Binomial theorem, which is my favorite. I love binomial theorem. Did I tell you guys? It's like the best thing ever. Do we have any questions on that? Because I mean, I'm pretty good, if I'm gonna be honest.
Yeah.
If like most of his stuff is the stuff on the homework, then we're solid. Like find the coefficient of like variable whatever. Vivian, do you want like an example on binomial?
Oh no, I'm okay. I was just saying what assignment 5 was. Sorry.
Oh, okay.
Oh, yeah, you're good. Thank you.
Okay.
You're good.
Do we have any questions on that?
I'm good on that, I think.
Yeah, I think I'm okay. Like the only thing that I can possibly think, see, it's just words for me. Like for instance, with the binomial or with the pigeonhole principle, like the idea of getting like selecting the right pigeonhole and selecting the right pigeons in order to get the n over k.
That's the hard part.
Yeah, because it's just trying to get the like, for instance, like the whole, like on the assignment, it's like how many meetings do you need to have a day with at least 2 meetings. I think I sat there for like the first 30 minutes just staring at the problem to try to make sure that I had the right like pigeonhole and the right pigeons in order to make it work. But in my head, conceptually, like I was thinking, okay, we want to have 1 day with at least 2 meetings. And then what I ended up like thinking in my head was like, but what if there's 2 meetings in 1 day? Nobody's telling me that I can only have 1 day a meeting. Is this something that I missed? Did I like not pay attention in class? And then like I paced a lot, and then I ate a sandwich. And Szumlanski said that would help, and it really didn't.
Yeah, those problems are asking, like, you know, what's going to force you to have that situation.
Yeah. Okay.
I guess it's like avoiding the worst case scenario, you know, because like you don't really want to have a lot of meetings in 1 day, so you're going to try to space that out. And so if you're like forced to have, you know, 15 meetings, then you have to have at least 3 meetings one of those days because you're forced to.
Yeah.
You could have more, but one of those days is going to suck.
Yeah, one of those days, like if spread out evenly. I think that's what I kind of wanted him to, like, you know, just like interject in there, like if spread out evenly, because that would have just solved it all for me. But,
well, because the question asks, like, what is the minimum number, or to guarantee it. So like that's the wording, is that, like, you know, what's the minimum required to make this happen so that you can't have it any other way, because, you know, otherwise you could have had, you know, you could have piled everything onto 1 day or whatever.
Okay. All right. Yeah, that makes sense.
Just making sure, problem 1D is impossible, right?
D?
Yeah.
Not with pigeonhole, yeah, it's impossible. On the homework, I solved it where I'm like assuming a meeting has to be at least 5 minutes long, and then I calculated how many minutes are in the week, and then I'm like, therefore, if we have meetings that last so many minutes consistently, then, you know, you'll die, but, you know.
Yeah, I did something like that too, to be kind of cheeky, and then I was like, oh, whatever, the TAs don't want to have to, like, read anything more than necessary, so it's just like, this isn't pigeonhole principle. Done.
I basically did this in mine. Okay, so now look at it.
Did you? Hold on a second. Is that your homework?
Yeah, pretty much.
That's beautiful. I should have done that.
Put that down. That's amazing.
I love it.
Yeah.
Oh,
yeah, that's phenomenal.
That's beautiful. I'm proud.
It's like the only chance that I can mess with TAs, man.
Oh yeah,
I'm sure they love that.
You gotta mess with the TAs, you know.
Who did you have? Like Harold, who graded that assignment for you?
Oh, let me see. Wait. Oh, it's actually Szumlanski.
Oh wait, are you sure, like, that's what the note was on there? Because, like, all of them are uploaded by him.
It is.
It would say in the document, the PDF document that was returned to you.
It didn't say anything.
Okay.
That sucks.
Yeah, I know a lot of the TAs, and so I was gonna go bug them later to see about that, but I don't want to ask them all willy-nilly. So, but anyways, I like to mess with them. I'm gonna have to do that at some point for like one of the other assignments. Funny GIFs. Well, not a GIF because it's a PDF. I take that back. Never mind.
Okay. Cool. So I think we're good on that. So yeah, there's at least 4 meetings on Tuesday. I don't think there's going to be a lot of questions on this because I feel like they're really easy. You know.
They'll probably be like the single questions. You know, binomial will probably be like a large choice maybe, and then the rest of the multiple choice is going to be like, you know, find the coefficient of blah. It'll take 2 seconds.
Yeah, it'd be like, okay, let me just do this real quick. We're done. Okay. There's not a lot. There's at least one even number selected, one odd number selected, given expansion. Yeah, that's really all I get. And then the Pascal's identity. I don't think he's. I don't think that's going to be in there.
We need to use it, he'll give it to us.
Yeah. I think the only like equations that we have to know are the ones for probability, number theory, and Euclidean theorem.
Yeah.
That one. Well, let me think if I have it in my head. So we take. Okay. Hold on. So let's say, for instance, we have the GCD of 233 and 186. We take the biggest one and try to find a number that will multiply into 233. If we can't find it, then it would be equals 186 times 1 plus whatever amount comes up to 233. And then we take the remainder, bring it down, and do the whole process over. No, I'm sorry, we take the 186, bring it down, and then take the remainder, and then do it all over again until we hit 1.
Oh, there's something important to note about that, too. I didn't realize it was an identity, and then Szumlanski's like, hey, guys, this is an identity. And I'm like, what? No way.
Let me see the identity.
This is a cool thing. So, and this is actually why the extended Euclidean algorithm works. So we have the GCD, right, of 233 and 186. And this is going to be A and B respectively, right?
Mm-hmm.
And so we do the extended Euclidean algorithm, and we get 233 is equal to 186 times by 1 plus some remainder, 14 plus 33 is 47, right? And so then it would be 186 times by so many 47s plus some other remainder. I'm not going to use B again, I'll use Y, right?
Mm-hmm.
Well, we know, right, these are the same. Oops. These are the same, right?
Yeah.
So this GCD is now equal to, of A and B, it's equal to B and the remainder, R. Like, these guys are equivalent.
Okay.
You know, whatever this remainder is. Because the new GCD becomes, I can scroll down, the new GCD becomes 186 and Y, right? Whatever, 47, I'm wrong, 47.
47.
That's the new GCD, you know? And
Okay.
so you notice that that's the remainder from over here. And these guys are equivalent because that's how we do the extended Euclidean algorithm. So, funsies to know.
Okay. Cool.
I didn't realize we could use that in equations, and that makes life a lot easier sometimes if you want to translate back and forth in proofs, you know.
Yeah.
I
Okay.
didn't explain that very well, but...
No. I think I get it. Like, you know, when you basically, whenever you're going through the iteration down in your Euclidean, each iteration becomes the GCD. Well, each portion of the iteration that you're doing to derive the next iteration can be equal to the GCD of the top.
Yeah. And that's useful when you're like, you know, how we were doing the proofs from before. Let me open a new page. So like we were doing the proofs before where it's like, oh, it only works for GCD though. So, but yeah, you're right. Yeah.
Okay. Cool.
So,
Let me think. Is there? You guys have any other questions about anything else that you're kind of confused about? Anything?
no. I think the only thing that was really weird was Bayes' theorem.
Yeah.
Like being able to translate it to words, but I think that's just thinking it through really slow. And then mostly just the probability. Like everything else really made a lot of sense. You know?
Yeah. Probability for me is probably the hardest one because you have to logic it, and
Yeah.
Apparently, I'm just not good with logic. So. Does anybody else have any questions? Vivian, chat. I know we only have one viewer now, but Harold.
I'm good.
All right, Rachel.
Yeah, I'm good.
All right. So I guess we're done. Well, that actually took a lot shorter than I expected. So, by about 30 minutes, which means that we're doing so much better because it took 4 hours last time.
Yeah. No, like last time was wonderful because Matt came on, right, and he explained the set proofs.
Pretty
And when
much,
he explained the set proofs, I understood it, and I'm like, oh, I get set proofs now. And then on the exam, we had a set proof, and I'm like, I bossed that so hard, it was amazing. I got like that portion, I got like perfect scores on that. So I was so happy.
Yeah, same thing happened. Same thing happened with me. Like when I did it, I felt so much better when I actually took the test when Fontaine came on. And then Zunessa said hi, and that was cool.
That was cool.
That was so much fun. Too bad they didn't come on this time. They're probably gonna come on like 12. They'll be like, "Where's everybody? What's going on, guys?"
I'm gonna go then because I have a lab at 5 tomorrow, so
5 in the morning?
I have to get up at 5 to drive to campus. Yeah.
Where do you live?
It's too far away for this to be decent.
I actually, you'll notice that I have a different setup. I moved from Kissimmee. I now live in closer to Orlando.
It's wonderful. I'm jealous.
It's so much better. Let me tell you, because Kissimmee is awful.
Like the neighborhood is awful, or driving through it to get to UCF is awful.
So, real shit. September. Okay. I'm about to go to work, and I'm just like, okay, let me just get my keys, go to work, and I'm on the phone with my girlfriend. I'm like, yeah, da 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 da, and I step outside. I'm like, where's my car?
They jacked your car?
He jacked my car in front of my house.
Oh.
I'm sorry, that's normal. Wait, that was this semester? That was today? That was recent?
That was last semester, yeah. Bye, Vivian. Thank you for hanging out.
I know.
Did you get it back? Like, did they find it, or?
Yeah, they found it somewhere in Orlando, and the door was messed up, and they burned my clutch because I thought my impression was oh, I can drive stick. Robbers cannot drive stick. And that is absolutely true, but it won't stop them from trying.
Right.
It sucks.
They really tried so hard that they got to Orlando and said, you know what, fuck it, we're just going to leave it here in this ditch. And then a tow truck company came in, and then they messed up the door. It was great.
I'm sure you love that.
Oh yeah, it was lots of fun.
As
I had
a
my
college
car
student,
back
we have
then.
lots of money, so you're able to just replace that lickety split.
Well, I mean, insurance is a thing, so that's nice.
Yeah, but they never give you the use value.
No. I had to get my car back, and they replaced the clutch. Which it was a $1,200 fix that ended up being only $500 because of my deductible. So
Okay, that's
not
pretty
terrible.
good.
Yeah. It could be worse. So, but yeah, don't live in Kissimmee. In fact, move as far away as possible from Kissimmee.
Okay. Thank you for the advice. Good night.
All right, good night. Night.